Just 1 second, so some network just will connect it. Just 2-3 minutes.
Hi, sorry for the delay. Actually, some Wi-Fi issue happened. So now I will present like a small introduction, like how we can do the hazard analysis in crisis, and like some example I will show you from this. So today I will show a demo of how the crisis software can be used for estimating. Voice is audible?
Yes, ma'am.
It's audible. No, the screen is visible. No, the PPT.
Yes, this is it.
It's right. Yeah. Okay. So today we will see like how we can do PSHA using crisis software. So when we are doing a site-specific study, our interest is like to obtain, as sir already told, different spectral acceleration at corresponding to or different values of PGA corresponding to different frequency of exceedance. So when we are if you are having like at a site, if you have K potential earthquake source, the frequency of exceedance of PGA can be computed using this equation, where like PM, PRM, and PY greater than Y star, these are like probability corresponding to magnitude, distance, and the ground motion prediction. Now, before going to the example, I'll show how, like, what are the typical steps in carrying out this PSHA. So first we have before one slide. So, like first step is like identification of potential sources. So at a site, what are like the sources? It can be a line source, area source, or gridded site or point source. Whatever we have to identify it first. Then we have to fit a recurrence relation. That is like what is the average rate at which a magnitude, particular earthquake magnitude is getting exceeded for a particular source that we need to estimate. Then we have to use a ground motion prediction equation, and that will give you like what will be the ground motion value for a particular magnitude and distance combination. And combining all this data, we can get the probability of exceedance for particular spectral acceleration value. Now coming to a software, when you are using, we have to model your sources in like in any of this, using any of these models. It can be a point source, line source, area, or gridded sources, and you have to estimate your seismicity parameter based on some models. So modified Gutenberg-Richter model is kind of common that we are using in this. And the ground motion prediction equation, you can give like default from the software itself, or you can give like attenuation table input as per your interest. And these are like some softwares which are like widely used. In that we are going to see arc crisis now. So first, I am showing an example similar to whatever video sir has sent. In that, I am having site of interest at 8025. This is my longitude and latitude, and I am considering a 500-kilometer region around the around that site. And I have identified that two faults are there, which is at 10-kilometer and 20-kilometer from that particular site. Now I have to, as I already told, we need to estimate first the recurrence relations for each of the sources. So after estimating, like with the previous past earthquake information, we can fit the log equation like this for regional recurrence relation, and we can estimate the parameters like A value, B value, and maximum magnitude for the particular region. And we will have this information for each of this fault, and using a slide for me. So using this information, we will start now with the crisis software itself. So I'll start here. First, I think already you might have downloaded the software and all. If you have not downloaded, you can go to our crisis software. You can type like this. Our crisis. Here you can see. Here you can see the download. Here you can get the software. After like inputting all the necessary details, you will get the download link. And if you want a tutorial, here they are providing with watch and learn session. There they are having 4 videos. Using that we can study, and they are giving an example data sets. So that also can be used for understanding. Now once you download the crisis software and install, the software will be like this when you open. So if you have a default files there, you can directly open it and give it in the software, or you can input each of these parameters. I mean each of the steps, whatever the information you are having, you can input and you can run the software. So as you can see here, maps are optional. If you have a map for the region, you can give. So I will start with grid of site. What is like if I want to do my simulation over a grid of cities, I can give the details here. Now I am doing it only for a particular site. So if I give the list of site, I have to double click and read the particular location here. So I have saved my city details in this. So it's not coming here. Not coming here. I mean, so can you stop it for something? Uh, just 1 second, some issues are there.
Am I audible now?
Yes, ma'am.
Okay. So I am showing my window here. I'll start from this. Okay. The screen is. Okay. So what I was telling is we need to give input to the board. I will open my PPT side by side. This is what I was about to tell. This is our example problem. Actually, you can see the site is there. From that 10-kilometer distance, I am having a fault A, which is able to, which can produce an average magnitude, earthquake of magnitude 6.5, and another fault, which is at 20-kilometer distance, and the magnitude that is associated with is 7. So this is one example problem. I think already sir has sent in a video, and you can see the output like a spectral acceleration at different periods. And now in this video, we are like going to see like how this particular spectral acceleration at various periods can be estimated. And that's what we are going to do here. I am having a site here, 8025. So what I have done is, starting I need to have a station file where I have given my station details. So I am having a city which is at 8025 longitude and latitude I have given. Now from that 500-kilometer distance, I have found that I am having two faults, and these are the fault coordinates. Now, after doing the recurrence calculations and all, I have the corresponding recurrence parameters for each of this fault. And after this, using a ground motion prediction equation, I can associate with each of these sources a particular attenuation relation, which will be of this form. And after that, when we are having all this information in our hand, we can find the, as already said, the hazard curve, which is the probability of exceedance for a particular spectral acceleration, say t equal to 0, 1 second, 2 seconds, like that till 10 seconds I am considering here. So when I am having equal probability of exceedance for all these at all these periods, if I get corresponding accelerations value, I can develop this kind of plot where it is like a uniform hazard response vector, its name. Now I am going to show you how it is done in crisis. So I have to give my grid of sites as input or list of cities. So I am giving here my input cities. So you can see here 8025, I have my station. Next is source geometry. So already we have two faults here, which is F1 and F2. So now I am going to add my faults here. So you can select which type of source you have to model. So first I am going to use line source only because we have two faults, and add new source. So my longitude is 80.12. 24.8, and I'm assuming it's like on the surface. So this is my first fault. You can draw and see here. So I have added my first fault, and I set it as alive. And if I want to add another, I can add another source, which is like line source, and that is at the distance 20 kilometer from the site, say 80.2, 24.5. So this is my second fault. You can draw here, and I set that also alive. So I am having two active faults. Source 2. So first, now we have given the source geometry. You can see here we have two faults in our region considered. Next, we have to give the source seismicity. So here comes the recurrence parameters. Whatever we have estimated, we have to input. So as said, we have two faults. So for first fault, you can give. I am considering Gutenberg-Richard model here. If you want to change the model, you can change the seismicity class here, and accordingly you can modify. So the threshold magnitude is 4, and the lambda value estimated previously, I am giving the same value here, and expected beta value, and coefficient of variation, and the magnitude is 6.5, and with an uncertainty of 0.5 I am considering now. For next fault also, threshold magnitude 4, lambda value I am considering same because I am considering both are in the same region. So reference parameters are regional I am considering, and both are like same I am giving, and 7.5 magnitude and subnet range of 0.5. So I am having now my two faults set with assigned with the seismicity. So once seismicity is also assigned, next we need to give the attenuation data. So for each, first I am considering here two attenuation relation, and I will be assigning it with each of the fault. So first I am adding model. Here you can give, as I already told, we can give a default model that is available in the software. Or here you are having another option, which is like attenuation table. We can input to the code also. So here I am taking two default models. Say NGA West 1 model. I am giving name as attenuation 1, and I don't know the fault mechanism and all. So as of now, I'm considering unspecified. And for 760 meter per second, that is for BC type boundary, I am interested to find the hazard. So I have given the VS30 value here. So that's my first model, and you can see the attenuation parameter and property. If you change here, you can draw how the attenuation varies and all. And I am adding one more model, that is attenuation 2. I am giving another NGA West 2 model. There are also fault type is unspecified and global, and VS30 760 meter per second I have given. And now I am having two models. So next we need to assign it with the source. So my first source is, I am having two sources. So I am giving like with first source, the first attenuation model, and for source 2, second model is given. So now it is assigned with an attenuation model. Next we need to give what are the spectral ordinates. So if you remember, I have told here, we need to, we can get like this kind of a plot where we need like different period of interest we can input. So as shown here, I am giving the same set of 11 time periods. So here this is like 11 periods are there. We can input here each of the periods, and this is like lower to upper limit that it will be calculated in terms of G. So those units and all mentioned here, and this 10 indicate like how many intensities are there. There it will be in a hazard band. So 0.01 I have, then this is my first intensity, and my second, I mean first period, then second is 0.05, 0.1 seconds, heat and 10 seconds. So I am having 11 spectral ordinates, and each of the periods are given. So once spectral ordinates are given, we can set the global parameters. Here, like how much radius of distance we are considering around the site. All those information will be there. And time frame I am setting to 1. So here you can see the return period and corresponding probability of exceedance in 1 year. So that after setting, we can save the file. So I am saving it like try to. So you can just cross check each of this. Like once we have given the site information, then these tabs also can be used. And this is like our site information, and this is our fault information. Source 192 we have, and this is like seismicity assigned to each of the. I mean that details will be. This is like geometry of the sources will be here, and how many spectral ordinates we are interested, that will be here. And here the seismicity assigned to each of the faults, you can see. If it is like a fault source, corresponding information will be there. If it is area or gridded, whatever be the model we are considering, correspondingly we can choose the model and we can give the inputs. And here the attenuation data will be there. So we have two attenuation models considered, that also is clear. And we have considered, this is like how the spectrum is going to be, I mean kind of median value. And here you can set the global parameter where I have given time frame 1 and corresponding probability of exceedance will be here. Now I have saved the data and now we can start running it. So once you run it, it's completed. Like as validation, they have, if some errors are there, that errors will be there. Warnings like associated with GMP, if it is not much problematic, then you can ignore that. And execution step, it will complete fast if you are having less number of stations and sources. And the results portion, it's like we have completed the simulation. Now the hazard maps option is there. Here you can see the option image. These are like different periods that we have input to the code. I am considering here the probability of exceedance as 0.0004, that correspond to return period of 2500 years. So when you click here, you can see the hazard curve associated with the PGA and the corresponding for 2500 years, what is the spectral acceleration or response spectral we are getting. So that information will get. So correspondingly, if you want like a for 75-year return period, you can change it here, and corresponding spectra and hazard curve we will get. Or if you are interested with some other period, then corresponding hazard curves also we can obtain from this. Now, if you want to import it if you want to export the details directly, you can save it and it will be directly saved to your system. So from that files also you can get the information. Now this is like one way of running. So another way is like if you have many many sources. I mean, now I have considered only 2 faults. Now see, if you can see, when I saved those files, it has saved into a .dat file. So here you can see, if you see clearly, the details whatever we input to the code, it will be written here. The city, where the city's information is there, and how many periods are there, and what are the attenuation relations we use, and the source information. All those details you can see here. Now, if you want to do it like for a more larger number of stations, you can edit it here, and you can import this particular file to the software, and you can run that way also. So these are another some files also I will show you, which will be come as output to the code. So you will get one .res file, which is like at each of the station corresponding whatever we have given the data, and outputs will be written here. And one GRA files also will be created after the program over. So this is like hazard curve at the city for different periods. So 0.01 or PGA 0.05, like that for all the periods. What are we give, like our given periods of interest, we will get the hazard curve. So from this also we can directly use this information for processing. So this is how you can use crisis software for finding out hazard at a particular point. But a site of interest. Okay. Great idea. Yeah. I will show one more example with grid of cities. Now I have given one particular site only. So when I am considering a grid of sites, what will be the output? Say for example, our region was 80-25. So I am considering the region 79 to 82, 79-24. I am considering with 0.5 increment. This is like a coarser region. Even if we want, we can make it final. So I'll just show how it is. We can make it final. So I am running it for different, grid of stations. So if you see the data, so you can see here, these are our two faults considered, and these are the PGA values. PGA values at that location as a contour you can see. So since it is like associate, I will change the return period as 0.4. If you see the 2475-year return period, our PGA value is like this, 0.78 G. Near the source, we can get a maximum PGA of 0.78 G, and you can see like as the distance increases from the fault, the value is coming down. So if you want like at a particular location here, you can get the corresponding spectral acceleration, hazard curve, everything. So this is how you can make some contour of PGA and spectral acceleration values. So you can see here with 0.2 seconds, our maximum value is 1. This happened because we have given the limit as 1. If it was given more, the values will be high. And 1 second, it is like 0.44 G. And like at higher periods, values are anyway obviously coming down. So this
So
is
you can see one interesting pattern. So like show for PGA, right?
this is PG.
PGA is this one. Now 10 seconds. So now what is that you observe, right? The contours, the color. So you can see, right, the contour shapes, they are entirely different for PGA as well as for 10 seconds actual, okay? So because I think the fault, what is the magnitudes? These two.
One is, the first one is like 6.5 and the right one is 7.5.
Okay, so now you can play with those numbers, okay? So like for example, if it is 8.5 magnitude, or generally what happens is long periods, is 10 seconds or something, they will be excited by higher magnitudes, okay? So small magnitudes will not be able to excite this high natural time period. So you can play, like you change it to 8, what happens? you change it to 5, what happens? You can try those things. Okay, so this you can apply. See, 8 you can increase it, Srija, that 8.
Yes, sir. Yeah.
Both the things you make it 8, and then you can say 10 seconds. Same, everything remains same, only the magnitudes.
Okay. Here I'll give.
Yeah. So both the faults now it is 8. Okay. Now run once again. Yeah. 2500 year return period. Okay.
Yes.
Now 10 seconds. Now you can see. Okay, some slight changes. So depending on the magnitudes, the frequency content, the higher time periods, and how the contours are looking like. Also, you can observe. So the faults are oriented like this. So obviously the maximum values are also in the same, the direction itself. Okay, so these are very important things. You can play with this software. Like variety of things you can try, like changing magnitude, what happens if the fault is nearby, what happens, far it is, what happens, and you can try all these things itself. Okay, so Srija, anything else is there?
No, sir. Like,
So, if any of you have doubts, you can ask right now. Okay, so all of you have downloaded, right, the software Crisis. So this
Yes, sir.
so this example, the slide says, Srija, we will post it in the WhatsApp. So you first do this, whatever example she has demonstrated, you just try to run it in the Crisis. Then I will send you one assignment. Okay, I will give you a list of faults or whatever, and then you have to run the Crisis software. So this same problem, whatever she has demonstrated today, you please run on your own, okay, in Crisis only, and try to get more or less the same result. So this is your first task. Then I will send you, a set of faults and other things which you have to run and compute the hazard curves. Okay.
Yes, sir.
So is it fine? So if there are any questions, you please ask me, okay, right now. And if you have any doubts in any issues running Crisis, I think Crisis you can easily run it in Windows. There is no issue at all. Okay, so you can easily run it, and you can. It's not a big deal. Okay. And Crisis is the, most of you may be knowing, is a software which everybody uses internationally, okay, to obtain the seismic hazard analysis. So this is a standard software, and we have also used to develop, the seismic zone map of our India also. Many things have been done with that software. So there are no questions. So if there are no questions, we will take leave. So this video I have recorded, I will post it to you also. So please run the same to same example. Then I will send you, maybe by this tomorrow, day after tomorrow, I will send you the exact assignment, what exactly you have to do. So I will be sending you some details, like for example, Bombay city, say, okay. So Bombay city, or maybe some Delhi city, I will send you the faults. So you have to get me the hazard curves, okay. You're using variety of GMPs and other things also. So that is going to be your major assignment, as far as this course is concerned. So this course is on seismic hazard seismology. So if we are able to run this software, and if we are able to compute the hazard curve, that means, and if we are able to run this Crisis and get the hazard curves, that means, this course has done justice actually. Okay, so that is a target for us. So is it fine?
Yes, sir.
So we will send you, please run it, and then I will send you the exact assignment. And that assignment is going to be a real assignment. It is not a toy problem. Okay. So you will be calculating hazard for a city, Bombay, Delhi. I will just sort out, the data and others, so that you have to do it. Okay. So if there are no questions, we take leave, and you please start practicing this one, and I will post you the assignment also. Okay. Fine. So have a nice day. Okay.
Thank you, sir.
Thank you.
Thank you, sir.